All right, section 2.5 ends with a discussion of the intermediate value theorem. And the intermediate value theorem is this. If f of x is a continuous function on the closed interval from a to b, then f of x attains every value between f of a and f of b. Let me draw a picture here. So I've got an interval from a to b, and I've got a function that's continuous on that whole interval. Everything, including a and b, that the limit as you go to that point is the same as the function value at that point. So let's say here's f of a, and here's f of b. I'm drawing f of b bigger than f of a, but it might be the other way around. It doesn't really matter. The point is, the function starting here at a height of f of a and it's ending there at a height of f of b, it has to pass through every height in between. You pick any height here that's somewhere it's going to get there. The thing is, if it's continuous at every point, I have to draw this without picking my pencil up, right? So any height you choose, I can say, oh, look, there it hit. This x value would give me that y value. Pick a different y value down here. You say, oh, here we go. That x value would give me this y value. For every single y value in between f of a and f of b, there has to be some x value that gives you that output. Okay. If you're bigger than f of b, you know, this I drew it actually got bigger than f of b. I don't know about that. The thing is, it might just be a straight line that goes straight from f of a to f of b, in which case, you know, you don't ever get bigger than 1 or lower than the small one. But at least I can guarantee you everything in between. Okay. This theorem actually got my dad kicked out of like 7th grade science class. Now, I haven't heard the teacher's point of view on this, but here's what my dad said happened. They're talking about orbits of planets and how they're elliptical. Now, I'm exaggerating the ellipse, but you know, here's the sun, and you know, the Earth is going around the sun in this ellipse, and that the average radius of the Earth is the orbit of the Earth is 93 million miles. Oops. 93 million. That sometimes the Earth is actually closer than 93 million miles, and sometimes it's further away than 93 million miles. And according to my dad, the teacher said, but maybe it's never actually exactly 93 million miles. In which case, my dad said, of course, this is my 7th grade dad, right? I mean, he's a kid, and he's probably a smart aleck. But anyway, he said, well, yeah, actually, it has to be exactly 93 million miles. In fact, twice every year it has to. I mean, he's picturing the graph of this thing saying, you know, at one point in the year, it's, you know, it's at its closest point. It's less than 93 million miles. All right, another point of the year, it's bigger than 93 million miles. And then by the end of the year, it comes back to that point again. He's looking at, you know, something like this saying, you know, if this is less than 93 and this is more than 93, then 93 million is in there somewhere, and I have got to hit it twice. You know, and you know, he said he was, you know, he must have done other things. It must have been like the last straw. I don't know. The teacher didn't like being corrected, and she kicked him out of class. That's what he said. That's the story he gives. But anyway, he's right. The Earth doesn't teleport. You don't suddenly jump. You know, you don't have breaks in the graph. You don't have an asymptote that you might approach going down and then coming back this way. No, it's a continuous function of how far away from the sun we are. Of course, then I'm going to have some theoretical physicists talking about quantum physics and how nothing is continuous, everything is quantum based. But let's not worry about quantum physics right now. It's a continuous function. You got to pass through 93 million miles somewhere. Okay. Now we use this in different ways. Here's one example. Show that here's a function, f of x equals x cubed plus 3x plus 7, not plus 7, sorry, just plus 1, has an x-intercept. intercept. Right. Now, I could actually try to say set it equal to 0 and solve, but cubics are a little trickier to solve than quadratics. But here's what here's what I want to do. Notice f of x is continuous. So let's say note f of x is continuous for all x. How do I know it's continuous for all x? Well, it's a polynomial. Polynomials are, the graphs of the functions. They're like a cubic. General cubic looks something like that. Maybe it goes down. Actually, it goes up because that's positive here. But you never have to pick your pencil up when you're drawing it. It's continuous everywhere. Okay. I also, let's see, I'm going to randomly grab a point here. Let's try plugging in f of 0. Just plug a 0 and see what you get. 0 cubed plus 3 times 0 plus 1. Well, that would be 1, which I'm going to point out is positive. Maybe you already knew that without me pointing it out, but I want to draw your attention to the fact that that's a positive number. I'm also going to try plugging in another point. Now, there's lots of different points I can plug in, and it may seem like I'm sort of randomly grabbing numbers, but I have an ulterior motive here. I'm going to plug a -1 in. So this would be -1 cubed plus 3 times -1 plus 1. So this would be equal to -1 minus 3 plus 1, which is -3. So what I've done here is I've said, hey, at x equals 0, this function is 1, and at x equals -1, the function is down here at -3. Okay. From -1 to 0, I've got a continuous function. It's negative here, it's positive here. 0 is in between those two, and so the intermediate value theorem says I have to cross through 0 somewhere, right? For some x between -1 and 0, f of x will equal 0. That's somewhere I'm going to cross over there. Okay. Now it doesn't tell me where, other than somewhere between my starting point and ending point, I've got an intercept. Now there are some computer algorithms that people have devised over the years for finding these things based on the intermediate value theorem. So for right now, I said I know somewhere between 0 and -1 and 0, I've got an intercept. And I said, well, maybe what I'm going to do next is plug in, let's say, a half. Figure out what f of a half is. Is it positive or negative? Well, if it turns out to be negative, then I'm going to guess a quarter next. Well, if that turns out to be positive, then I'm going to guess, in between. And so there's this algorithm called the bisection method of taking your interval. You get an interval that your solution is in, so we know that the intercept is somewhere between -1 and 1. Then you cut that interval in half. You try the midpoint, and that is going to determine which side you need to go. If to say negative and negative, that doesn't guarantee me anything, but to say negative and positive, it's like, all right, you're somewhere in between. So I grab the middle. Actually, in my thesis work that I did, I was working with, I was building these donut-shaped polyhedra that were made from folding paper, and I had to show that they existed. I had to show that the way I was putting them together actually worked. And so I had these equations that I had to solve, and essentially solving systems of linear and quadratic equations. But I would work on this stuff that there'd be like this zigzag fold pattern that would come down here, and going around the other way it would come up here, and I had to show that this actually matched. And so I'd show that for some values of some, I'd be guessing at initial coordinates of certain points, and sometimes when you worked all the way around, you'd have guessed wrong, and they cross over, that they didn't line up exactly right, that this one was bigger than that one. And for other initial starting values, you'd calculate around, and they wouldn't quite get together yet. And so then I could argue from continuity that if I miss this way for one value of my starting variable, and I miss this other way for another value, that somewhere in between I must have had it just right. And I made these kinds of arguments lots and lots of times, and devised algorithms for computing what these folded things look like. In fact, I'm going to pause for a moment, and then I'm going to point my camera over at my shelf here and say, these are the kinds of things that I did. You can see all the folded stuff in there. That's what they gave me a PhD for, folding paper. But those donut-shaped ones were calculated essentially using the intermediate value theorem and a bisection method to say, I know they fit somewhere, and then I just had to keep guessing closer and closer and closer until I got enough accuracy to plot and build those things. So anyway, the intermediate value theorem. There you go. I hope you don't get too dizzy.